Hi, this is the last of 6 introductory videos to high school chemistry. This one is on how to measure things. Chemistry is a very experimental science. Now, there are theoretical aspects to chemistry, but since chemistry has to do with the changes and the way in which matter interacts with other matter, and the way in which matter changes, and the way in which matter interacts with energy, this is a heavily experimental science. So you're going to have to measure things. And so, when we measure things, we make a distinction between something called accuracy and something called precision. Accuracy has to do with whether or not the measurement is right or wrong. So, for example, I'm 5 foot 11 inches. Well, at least that's what it says on my driver's license. I have a feeling that as I approach 50 years of age, I'm getting slightly, I don't know, curved, or I'm shrinking, or I'm not quite sure what. But I'm still 5 foot 11. At least I round to it. I'm sticking with that. Maybe in 10 years I'll be 5 foot 10. I hope not. But let me say this. I am not 4 foot 11 inches. I don't care who told you that. It's wrong. I am 5 foot 11. You know, maybe I'm 5 foot 10. I don't know. I don't think I'm 5 foot 10. But it would be completely inaccurate to say that I'm 4 feet tall or that I'm 5 feet tall. And yes, it would be inaccurate to say that I'm 7 feet tall. Those are simply wrong measurements. I am in the neighborhood of 5 foot 11 inches. Now, you might say that there are greater and lesser degrees of precision about how tall I am. Precision has to do with how exact a measurement is it. Is it precise to the 10th, or to the 100th, or is it precise to the 1000th? Now you could, if you were just kind of rounding off, you could say I'm about 6 feet, because I'm certainly closer to 6 feet than I am to 5 feet. And so depending on how precise you're being, you might say that I'm 6 feet. Now you could be a little bit more precise than that and say that I'm 5 feet 11. Maybe I'm 5 foot 10 inches, 10.6 inches. That would be even more precise. I just made that up. But that would be a more precise measurement. You get a sense of what precision is? Precision has to do with how exact the measurement is. Accuracy has to do with whether or not the measurement's right or wrong. Now here we get into the question of significant figures. How many of the figures, how many of the places in your measurement are actually real, and how many of them are approximations? Is there one significant figure? Are there 2 or are there 3 significant figures in your measurement? It doesn't really matter where the decimal point is. How many of the figures of the places in your measurement are the real ones? And, you know, you might get some reading on a scale of 26.5, 6, 7, 8, 9, 10, 11, you know what I mean. But how many of those are actually significant figures, and how many do you just need to disregard because they're not real at all? There is, they talk about error, within a certain error. Significant figures are the parts that aren't in error. There are some basic rules for significant figures. So, first of all, non-zero numbers are always considered significant. Not in the measurement, but when you report them, or when you're reading, about someone giving you a number, the numbers that are reported, the numbers that are there, are all significant if there's a number there. So, 2,345.34 has 6 significant figures. So, when you have a number, non-zero numbers are always considered significant. And of course, if there are zeros between the numbers, those are also considered significant. Secondly, if there are any zeros given at the end of a decimal, like if you're reading in a problem that a number is 34.200, those 2 zeros, they wouldn't have put those there in your problem if they were not considered significant. So this has 5 significant numbers, 34.200. Now, if it was 34,000, then those 2 zeros before what would have been the decimal point are not considered significant. 34,000 is considered to only have 2 significant figures. So those, if you have 1 million, and you have 6 zeros after the 1, it's only considered to have 1 significant figure. Those zeros before what would have been the decimal point are not considered significant. Similarly, space-holding zeros don't count. So in 0.0043, we say there are only 2 significant figures. Those zeros that are kind of placeholders, space holders, before you get to the 43, they're considered they're not considered significant figures. So 0.0043 is only considered to have 2 significant figures. Let me end with scientific notation. Scientific notation basically focuses in on the significant figures and then uses a 10 to a certain power to go for all those zeros that aren't significant. So 10 to the third power is a 1 with 3 zeros after it. That's 1,000. So if I multiply 7.09 times 1,000, what am I going to get? I think I'm going to get 7,090. But there's only 3 significant figures, and so scientific notation hones in on those significant figures, the 3 figures here being 7, 0, and 9, and then uses 10 to a certain power, 10 to the third power meaning 10 with, or 1 with 3 zeros after it, to kind of tell you what the insignificant zeros that come after that number. It's a way of writing very large numbers without having to write them all out. So a googol, not Google, but a googol, G-O-O-G-O-L, is 10 to the 100th power. That's a 1 with 100 zeros behind it. That, you wouldn't want to have to write that out, would you? So by saying 10, to the 100th power, it's a shorthand of writing without all those insignificant zeros. Well, this has been a video on measurement and things like accuracy, precision, significant figures, and a little bit on scientific notation at the end.